All right, today we're going to dive into a concept that is absolutely fundamental to modern engineering, but it's often hidden in plain sight. We are talking about the fixed bed.
You might not even realize it, but the simple idea of flowing a fluid through a bunch of packed particles, well, it's happening all around you. It's kind of the unsung hero behind countless industrial processes that make the stuff we rely on every single day. So, that leads to the big puzzle for engineers. Imagine trying to push water through a big jar just packed with marbles. How do you predict what's going to happen? How much force do you actually need? That's the essential question we're going to answer. Okay, so first up, let's pull back the curtain and see exactly where these fixed beds are the star of the show. I think you'll be surprised by just how common they really are. And wow, their versatility is just incredible. We see them in these massive catalytic reactors, which are crucial for making all sorts of chemicals. They're in drying columns that use things like silica gel to pull moisture out of the air. They're used in huge towers to absorb gases, and maybe most familiar to you, they're in all kinds of filtration systems, from industrial water purifiers to maybe even the filter in your fridge. All right, let's get to the main challenge here. See, forcing a fluid through that maze of particles, it isn't free. There's a cost, and it's a cost that engineers spend a whole lot of time calculating. I want you to imagine trying to move through a really dense crowd of people. You have to push way through, right? And you feel that resistance from all sides. Well, a fluid experiences the exact same thing. Every single little particle it has to flow past creates a tiny bit of friction, a little bit of drag. So in engineering speak, we call this resistance pressure drop. It's the total loss of pressure from the moment the fluid enters the bed to the moment it leaves. The bottom line is this. If you want to move that fluid, you have to apply enough pressure to overcome this drop. This is like the number one thing we absolutely have to predict. So how in the world do we start predicting that? Well, before we can even touch the pressure drop calculation, we first have to understand the character of the flow itself. Is the fluid moving in these smooth, predictable layers, what we call laminar flow, or is it tumbling and mixing all over the place, which we call turbulent flow? And why does that matter? Well, the answer completely changes how we do our math, because chaotic turbulent flow creates a lot more resistance. To figure this out, engineers have this incredibly powerful tool called the Reynolds number. Now, what's so cool here is that the standard Reynolds number you might have learned for a simple pipe, that won't work here. No way. This is a special version, one that's been modified specifically for the complex, twisting journey inside a packed bed. Okay, let's break this down real quick. Don't let the symbols scare you. We've got fluid density and viscosity, basically how heavy and thick the fluid is. We have superficial velocity. Just for a second, picture the bed was totally empty. This is how fast the fluid would be moving. And then you have the properties of the bed itself, the size of the particles, and the solid fraction, which is just a fancy way of saying how much space is particles versus how much is empty gaps. You mash all that together, and you get one simple number that tells you everything about the flow. So, once we've got our Reynolds number and we know for sure that our flow is nice and calm and laminar, well, then we can bring out the big gun, the equation that solves our pressure problem. This is it. This is the Argon equation. This formula connects all those things we just talked about, fluid viscosity, velocity, particle size, the length of the bed, and lets us directly calculate that frictional pressure drop. This right here, this is the key that unlocks the entire design. All right. Theory is great and all, but let's make this real, shall we? We're going to walk through an actual engineering problem and see exactly how these tools work in the wild. Okay, here's the setup. We've got a gas, and we know its density and viscosity. It's flowing at a certain speed through a bed of a specific height, and it's full of particles of a known size. Our job? Find that pressure drop. First things first, we got to figure out what kind of flow we're dealing with. So we take all of our known values, the density, velocity, particle diameter, viscosity, and we just plug them right into that special Reynolds number formula. And boom, we get our answer, 3.125. Now, since this number is super low, and typically anything under about 10 is considered laminar, we know we're dealing with that calm, orderly flow. If the number was way higher, like in the thousands, we'd have turbulence and we'd need a different equation. But since it's low, we get the green light to use our Argon equation. Okay, now for the grand finale. We take all those same variables and we substitute them into our pressure drop equation. Now, I know this formula looks a little intimidating, but trust me, it's really just careful arithmetic. We're just plugging in the numbers we already have to find that one missing piece of the puzzle. And
There it is, 116.6 pascals. That is the exact amount of pressure that will be lost as that gas travels through that 3-meter-tall bed. Now an engineer can take this number and pick the perfect pump or fan for the job. And just like that, problem solved.
And this is the real beauty of it all. That whole process, the ability to design a massive, complicated industrial system, it all boils down to understanding and correctly applying one elegant, powerful equation. It's just a perfect example of engineering principles in action. It really makes you wonder, doesn't it? What other seemingly chaotic, complex systems out there in our world are just waiting for their own elegant equation to be discovered? Thanks for digging into this with me.